Okay, for today we are talking about different ways of looking at multiplication. So that's still 1-3, and hopefully we are going to start 1-4 today, which is topic of matrix inverses. Okay, we talked about matrix multiplication. We said, well, it's a mass of work to do. It's not a fun thing that you choose to do on a weekend or whatever. A lot of multiplication and addition has to be done. Well, you want to be systematic about it. You want to choose some way of doing it. And there are different styles. And some of these styles have a special meaning to them. So we want to take a look at the possibilities. So what was the basic definition we had? The basic definition we said, if you have a matrix times another one, they come in blocks. And the output is some other matrix which you obtain by spending quite a bit of time. What was our approach? Our basic definition was to take a row of this one and multiply that with a certain column of this one until you get a number. You do a dot product, and whatever that product is, you write it in a location where the row location of this entry is inherited from the row location of the first one, and the column location of that is inherited from the column location of this one. So if this was on the row I and this was column J, this entry is going to be sitting at the row I and the column J. The multiplication of this yellow with the green is going to be done just like you do dot product in physics. You multiply corresponding entries and add them up. We justified that or gave motivation for it for going to shopping, buying a certain number of certain things. You want to know your total. You multiply how much you have spent by how many items, you multiply the price by how many items you bought, and then you add them up to get that particular total. So that was our definition. Now you have to do this thing over and over again, and when you have a task that is that repetitive, you want to do it in a systematic way. Like if you are raking the yard, you decide to rake in a certain way perhaps, and then rake all of them at the end in one other direction, make another sweep, and so on and so forth. With matrix multiplication, the task is somewhat similar. So we essentially are looking at matrix multiplication in a block style. So we are going to take our matrices and kind of break them up into blocks, and then handle separate blocks until we are all done. Kind of the way you might clean up some warehouse. You go by rows and then you go to another row, as opposed to doing things randomly. Okay. One simple way of describing the situation would be that you have your matrix A. You might say, okay, I'm going to consider this big pile of stuff here. I'm going to take my matrix B and I'm going to think about it as a bunch of columns. So that matrix B that you have, it is made out of several columns. So you want to perhaps say that clearly, that there are a bunch of columns here. And then you might decide to say, I take the matrix A, multiply by this column. That itself entails a lot of work. You still have to do whatever we agreed to do before, But your approach might be that, okay, I break this up into columns. I take this matrix A, multiply by this column. That's going to give me some column here. So you multiply that with that column, it gives you a column of the answer. You multiply your matrix by the second column, then you write down your answers here. Multiply by the third column, and you have your answers there as well. So this is you are doing the matrix multiplication in a by breaking up your second matrix into a bunch of columns and doing it like that. Another style you could do, well, you tell me what do you think is the other possibility. So you have this matrix A, you want to multiply. So I take my matrix A, first one, and break it up into a bunch of rows. I take this row, multiply with the matrix B. How do you do it? Just the way we define how you do it here. You have to take that row, multiply by each of the columns, do a dot product, and get an answer. But here, you're just suggesting how to go about doing all of that messy stuff. You take all of this row, multiply with the second matrix B, that's going to give you a row. Take the second row, multiply by B, that's going to give you another row. Third one, multiply by B, that's going to give you another row. So that would be another way of going about our business. Another view that we might have is to split up A and B to rows and columns simultaneously. To make this thing a bit more specific, perhaps I go ahead, pick particular matrices. Let's say A is, now I'm just going to stick to 2 by 2 so that we don't spend forever writing stuff. Of course, our ideas are applicable to larger matrices as well. I can take matrix A, break it up into its rows. Okay, this is essentially one of the rows. The other one, I just kill everybody there. These are all zeros. So just erase them. This one is the second row. I have just erased everybody else, and my matrix is officially been looked at as 2 matrices, essentially the 2 rows that we have. We play the same game with B. We say B, well, I take the first column, erase the second column, and then second time around I erase the first column and just keep the second one. So here are the columns. Now when I want to multiply A with B, how do you multiply? I have to multiply this matrix with that one, this matrix with the second one, the second matrix here, second yellow one with the first green, second yellow with the second green, and so on. So let's write it out, just as in Algebra 1, if you had, say E plus F times G plus H. How would you have done that? You would have voided, say, this times that one, then this one times the second one, this one times the first one, second one times the second one, and so on, and you write down all the multiplications you could conjure up. You do the exact same thing here. So when I want to multiply, I'm going to have the first yellow one times the first green one, the first yellow one times the second green one, the second yellow one times the first green one, plus the last round we have second yellow one times the second green one. Now what do you think each of these things is going to be? Still we are multiplying the way we said our official definition, whatever it was, that's what we are going to be using every time anyway. Except that some nice things going to happen. When I multiply these guys, what is the only non-zero entry? Is that right? When I multiply this yellow with that green, what am I going to get? That is AX plus BZ. What is in every other location? Yeah, this is multiplying entire zeros. So that's going to be 0. This row is 0, so you multiply whatever you want, that's just 0. So this is simply explicitly telling us that when that row is multiplying by that column, the answer is going to be written in the first row, first column of this. And then as I go ahead, I am going to have 4 matrices, each of them created in same style. We just see explicitly where everybody is going. So let's try it. When I multiply this with that, where would the location, what's the location of non-zero entry? Yeah, so, say it again. This is the first row, second column. Okay, so I'll get AY plus BT. When I multiply by the first column, I'm going to get the 0 here. This 0 times any of these columns is going to be 0 entries. And so on. So this is going to be like CX plus DZ, but the first row being 0, you multiply by those columns is 0. You take this row, multiply by that column, it is 0. And finally, what's the only non-zero entry of this last matrix? Second row, second column, is that right? CY plus DT, and these guys are just zeros. So we can think about our matrix multiplication that we were talking about here. If you wish, you can chop up your matrix A to a bunch of matrices, matrix B to a bunch of matrices, and perform this. When you want to put all of those entries into one matrix, you see what we have seen before, that is, this is AX plus BZ, first row, first column. This is first row, second column. And then this is second row, first column. So here CX plus DZ. And here is the second row, second column. So CY plus DT. Okay, so that wasn't all that exciting. We just put everything back. More interesting thing happens if you do this thing in a different way. What if I take the columns of that, multiply with the rows of this one? Columns of this times rows of that one. That's kind of where we ended up last lecture. Let me just refresh your memories as to where you had seen this thing. So over there we said if you have a column, let's say 1, 2, 3 times a row, over there we chose 10, 100, 1,000. When I multiply these two, what do I get? What does it look like? You get a full matrix. That reminds us of multiplication tables back in elementary school. You just multiply this column with that row. You have a huge number of numbers here. You just well, write them down. So if you have column times a row, what you get is a full matrix, which reminds us of the multiplication tables in elementary school. Here they have another name for it. They call it outer product. So this kind of activity is referred to as the outer product of two vectors. Okay, what is that going to do for us? What we have in mind is that we take our matrix A and matrix B. We want to know what we can extract out of this if I break this into columns and break the other one into rows and multiply the columns with the rows, just like I would have multiplied these multiplication tables. And we are going to see that if you multiply each row with its corresponding if you multiply each column with its corresponding row and you just add them up, you get the same matrix multiplication as before. So A times B is going to be turning out to be, let's call these guys column 1, column 2, column 3, row 1, row 2, row 3. So column 1 times row 1 of the second matrix, column 2 times row 2, and so on down the road we go. So this is called multiplication by using outer products. Let's see what's the reason for that. So I take again an example of a 2 by 2 matrix so we are not drowned in writing lots of so I have A, B, C, D times X, Y, Z, T. What I do instead of that, I'm going to write this as, I'm going to break it into columns. AC 0, 0 plus 0, 0 BD. Okay, this is same as that. So it's as if I'm breaking that job into a bunch of columns. This one, I'm going to break it out according to rows. So I'm going to multiply all the green ones with all the blue ones. That's the job that we have for ourselves. These are all the greens. These are all the blues. They are just representing our matrices. Now something interesting happens. When I multiply the first green with the first blue, help me out with that one. What kind of multiplication is it anyway? Here's a column, here's a row. That multiplication, we called it what? Outer product. That's an outer product. So let's do an outer product of column 1 of the first with the row 1 of the second. What am I going to get? So A times X, A times Y, C times X. So I took that. Now really, if you want to do complete job, you have to say A0 times X0, that's just AX. A0 times Y0, just AY. C0 times X0, that's just CX. C0 times Y0, that's just CY. So instead of going through all of that, we just call it out like a multiplication table. A times everybody, C times everybody in the second row, and so on. Now, tell me what happens if I multiply. So we call this thing column 1. Let's call it column 1. This is column 2. This is row 1, really. This is row 2. Meaning everybody else has been zeroed out. So I did, this was column 1 times row 1. Now let's do column 1 times row 2. What happens? If I multiply this with that, what am I going to get? In your mind, multiply this green matrix, the first one, with the second blue one. Tell me the entries of what I'm going to have here. take this matrix, this green matrix, multiply with this blue matrix. So let me just mark it out so that let's focus on this. This times that. Ignore everything else I've said today. Just multiply these two matrices like we did last time. What are you supposed to do? Multiply them. No. Multiply these two. Tell me what you get. You said what? No. Again, forget what I said today. Just multiply this yellow stuff with those yellow stuff. 0. Is that right? A times 0, 0 times z. Now multiply this yellow with the second yellow here. Does everybody see? A times 0, 0 times t, that is 0. Second row times the first column, 0. Second row, second column, 0. When the column number and row number don't match, they just all fall apart, it all becomes 0. Let's try one more time. Who else I have to multiply? This is just idea of foiling. So I multiply column 2 with the really row 1, column 2 matrix times row 1 matrix. So take so here we are focusing on these two now. What do I have? 0b times x0. What is the net? 0. 0b times y0. 0d times x0. 0d y0. Now, for something that makes some contribution, let's try column 2 matrix times row 2 matrix. Now they multiply 0b times 0z. Who's that? 0b times 0t. 0d times 0z. 0d times 0t. So this was for us the column 2 row 2 matrix. So these guys don't play any role. Now if you put all of your matrices together, you get ax plus bz, like ax plus 0 plus bz, ay, bunch of zeros plus bt, cx plus dz, and cy plus dt, which is what you would have gotten by multiplying these in the normal way. You might ask, why do this? You know, we learned it one way, why do it another way? Several reasons. One is, well, we are going to see hopefully today an explanation of matrix vector product. This is going to give us a different flavor for it. The second reason is that when you are doing computer programming, if your computer might have several cores to it. These cores, you might try to break up a job and farm out different portion of the job to different cores of the computer so that they all go attack a problem, collect the answer, bring it back, and then you put them together, as opposed to a sequential operation where you just wait for one little thing to happen and the next little thing to happen and the next little thing to happen. That's not very effective. If you can kind of write your computer program so that you kind of branch out, do several things and bring them all back together at the same time, you can make your activities to run a lot faster. So different ways of dealing with matrices could help with our computer programs. It's also important conceptually, and we are going to do one of these concepts. So the lesson of this view was that if I have a matrix times another one, let's go back here, see what happened. Essentially what happened here was that the column 1, this column 1 multiplied with this row 1, that was the contribution here. And then we had this column 2 multiplied with this row 2 according to that table style multiplication, and that was a contribution here. Then we added them up. So that's the reason for what we wrote here, that you take the column 1 multiply by the row 1, you have a full matrix. Then you go 2 and 2, you have a full matrix, and 3 and 3, you have another full matrix. But you don't mix and match. You don't have like 1 and 2, or you don't have 2 and 1, and so on. Those things are just zeros. You don't need to bother with them. Unlike the previous style. In the previous style, you had to take care of everybody. Everybody was making a contribution. There was somebody here, somebody here, somebody here, somebody here. There were no matrices that was entirely zeros. Okay, everybody was making contribution. But we turned the table around. Some of the matrices turn out to be zero, so we don't need to worry about them. And that gives us the reasoning for this. You multiply a column with a corresponding row, another column with its own corresponding row, and so on. So let's emphasize this point one more time. So we take this one, break it up into columns. We take the second one, multiply, break it up into rows, and then if you wish to name them 1, 2, 3, 1, 2, 3, you multiply one of this with one of those, just the way you would have done a multiplication table back in elementary school. So you say this result is column 1, row 1, which has to be done just like a multiplication table, and then you repeat column 2, row 2, and in as many of these things as you got. They should of course match for you to even contemplate multiplication. So then we call this thing outer product style. Okay, so if your workers inside your computer and your cores, you can assign this job to one core, that to a second core, this guy to a third core, so all the cores are busy doing something, then you bring the answers back. Okay, a special case of this, to show that special case, let me just make a small matrix here, A, B's, let's see. Suppose I have this matrix, and then I am multiplying it with X, Y, Z. So it's a special situation. We have one matrix. This is going to be just roll of this yellow one, if you wish. And the second one is just a narrow matrix, just a column. Well, let's go ahead and do this two ways. One is our old style. Our old style was to multiply AX. So I take that row and this column, AX plus BY plus CZ. And the second times this column is DX plus EY plus FZ. And the third one, GX plus HY plus IZ. I notice that here all the X's show up, and Y's are showing up here, and Z's are showing up here. That gives me an idea. Say, okay, I can look at this problem like this. As if I had an X, the first entry, I multiplied with that entire column. And this Y, the second entry, I multiplied by second column. And this Z, I multiplied by the third column. stare at it for a while, you see that's exactly that idea that you had over there. That take that entire column, here's I'm taking that column, multiply it by row 1. It just so happens that row 1 is just one number now. So multiplying this column with that row is going to be one piece. Multiply second column with that row, which is just one number, is the second piece, and the third one. Now, this right now it looks like we are just juggling terms around. We're just doing multiplication, addition, and keep rewriting the same thing. But a philosophical way of looking at what is happening here is that the result of this multiplication is a linear combination of the columns of the first matrix. That is, you are taking the first column, multiplying by some number, second column multiplying by some number, third column multiplying by some number, and these numbers are extracted from here. The kind of a configuration that shows up here is called linear combination. You remember at the beginning of the semester we talked about what is linear and what is non-linear. So linear meant you multiply your entities by some numbers and add them up. So the philosophy that is being applied here is that these are your entities. It's like a package of gifts or such. Maybe in that package of gift there are 8 Cabbage Patch dolls and D trucks and G.I. Joe soldiers or something. And they're making a package of that. You say, I want 3 of this package, perhaps 2 of this other package, and 11 of this third package. These are acting as packages for you. And this is how many of them you are ordering. You're saying, give me an X of the first, and a Y of the second, and Z of the third. So this gives you a flavor on how to handle multiplication of a matrix by a column vector. Now, well, if you have another column, then you have to go back to this full version that we had over there. So perfectly okay question. Like if you had here the question is, what if I had more stuff here? Like I had A, B, C, D, E, F, G, H, I, and here I had X, Y, Z, and say T, U, V. Anything special about that? Well, yes, you can go ahead and write it. It's just doesn't show up all that much significantly later on for us to emphasize. This shows up a lot more later on because it matches the way we write equations. This one, well, if you want to do that, what do? Our recipe was to take that and this, multiply just like matrix multiplication. So you go on the right hand side, say I have to take A, D, G, multiply it by X, T. So this is this is like a multiplication table where you have 3 numbers here and 2 over there. You have to multiply all 3 with all these 2 and just make a table. There will be 6 numbers here. Then we said you take the second B, E, H, multiply with the second row here, so that's going to be Y, U, and then the third and the third. So C, F, I, Z, V. So this is again a table by itself, 3 by 2. You have to do multiply all of these guys with all of those guys. So you'll have 3 tables, each of them having 6 entries in it, and then you have to add them all up. Now, special situation here is that if this is a single number, well, you can write it anywhere you want, on the right, on the left, inside, wherever you wish. That's all fine. It doesn't make any difference. Anything more complicated than that, we have to go back to the matrix notation and just do it like that. Okay, so you read the examples in the text regarding to this kind of multiplication and try to kind of practice as much as you can. We are going to go to section 1.4, which is matrix inverses. So what do we mean by inverse? When you study mathematics, whatever operation you learn, you want to be able to undo it as well. Okay, sometimes you hammer a nail into an object, sometimes you want to pull that nail out, so sometimes you want to undo an operation. What are the basic operations you do in math anyway? You have addition, and the other one is multiplication. So what is the opposite of addition, or inverse of addition? So that would be your subtraction. Is that right? So if you have, what's the idea of subtraction? Or that gives you the idea of a positive and negative numbers. If you have a number 2, you add -2 to it, you get what you call the identity element of addition, big name for 0. Multiplication also has an inverse. What is that? We have a division. So if you have a number 2 that has an inverse with the property that if you multiply them, you get the so-called identity element of multiplication. Again, a long name for just 1. Now when it comes to matrices, that was trivial. This is an industry all by itself. You'll just notice how complicated multiplication was. You have to wait until you see division, that it becomes 1 degree even more complicated. So just to review, operations that we have in mathematics: addition, subtraction, multiplication, division. We have, of course, exponentiation and composition. You have 6 operations to deal with. These were kind of things that were trivial. You add and subtract as comes naturally. This one, we spent a week on that one. This one perhaps is going to take a month to learn about division. So let's see. Very first time in elementary school you learn about division, they always start with a pizza for some reason. So here is something, you want to divide it to 3 people, and of course you have the notation of 1/3. So 1 indicates the whole thing, and this is how many pieces you want to divide it to. Okay, we said something about the role of 1. Who plays the role of 1 in linear algebra, in matrix analysis? Who played the role of 1? Role of 1 is played by what? What matrix was it that had the same property as 1 does in elementary arithmetic? Elementary arithmetic, 1 has the property that if you multiply by anything, you just get that thing back. The identity matrix plays, so we say identity. Who was the identity matrix? Identity matrix had a special look to itself. 1's in what location? Yeah, these are called. This is called the main diagonal. Second diagonal doesn't play much of a role because of the way we write stuff. Up here is supposed to be all zeros, just so that we don't spend so much time writing all these zeros. We just put a big 0 there indicating we have all zeros in that location. So of course identity matrix depends on what size you want it in. You want a 2 by 2, 3 by 3, and so on. You just stretch it as much. Sometimes they show it by I with a little n underneath it. So for example, I2 would be identity, which is a 2 by 2 matrix. Identity matrices typically are taken to be square matrix. What do you mean square? Square means, well, the sizes are the same on both directions. So what we really want to do is to divide. We want to take an identity matrix. Well, in you go to algebra 1. What's another notation for 1/3? You write it as what? 3 to the power of -1. Is that right? So here, instead of taking identity and writing identity divided by a matrix, we choose this other notation, which has its own problems, but a to the power of -1 is going to be the notation for inverse of a. Okay, what did you expect out of your inverses in elementary arithmetic? We said inverse has a property that if you multiply by the original, you get the identity. Like 3 times 3 inverse, the main claim to that is that when you multiply them, you get 1. Like 3 of 1/3 slices is a whole pizza. Here we have the same definition, that the inverse is a creature, that if I take my matrix and multiply with it, I get the identity. Now something starts to nag at us at the back of our mind, that matrix multiplication made a difference, who goes first, who goes second. Does it make a difference here? Well, we hope not. That either way that you multiply them, you better get the identity. So inverse of a matrix, if it exists, is a creature that if you multiply with the original in any order, you are going to get identity. Now another headache comes up. In elementary arithmetic, they tell you you can find the inverse of anything except for one number. What is it that doesn't have a defined inverse? Yeah, 1/0 is not defined. We expect that for certain matrices, its inverse will not be defined. For certain matrices, inverse is not defined. So matrices divide into 2 groups, and the situation is not as easy as it was in arithmetic. In arithmetic, there were just 0, you know, here's my 0, and everybody else went to the other camp. But here, the guys who don't have an inverse, they are a big camp all by themselves. And figuring who is it that falls into this camp, who falls in the other camp, is not going to be as easy. So we have two camps. One is called invertible, which means has inverse, and the other camp is going to have lots of names. One of them we might use right now, sometimes called singular, but there's going to be a whole slew of names that we are going to talk about. Okay, so you of course suspect that if a matrix was entirely made out of zeros, it's not going to have an inverse, but that's not the only one. Okay, so if you have a matrix of entirely zeros, no matter what you multiply this guy with, you're not going to get an identity. So you cannot find an inverse for this guy. But there are plenty other ones where they are not as trivial as this, but they don't have an inverse either. And that's going to create a headache or point of interest for us. We are going to talk about that. So you want to finish section 1.3. You want to read the end of it. You have to read all the examples in the text. There are not that many exercises there that is going to ask you for those concepts, but read entire 1.3, do all the problems of 1.3, and start reading section 1.4. In section 1.4, linear algebra is going to kind of take off. Things are going to become a lot more complicated, so you want to read ahead before we give a lecture. Good luck and all bless. Yes? I will let you know on Wednesday for the list.